Hi class, we are on to the next section, chapter 3.3. Today we're going to talk about dividing polynomials. Now, when we talk about dividing polynomials, we're going to show two ways today. One way, just so that you're familiar with the division process, and then the second way, which is the method we're going to use most often in this course, although you do need to use the first method from time to time because the second method does not always work. It just works for the majority of cases that we will be dealing with. Okay, so basically what we're going to start off with is long division of polynomials. So to help us get started, I suggest you pause right now and you make up a long division problem, right? A regular, standard, I don't know, let's say 384 divided by 3. Okay, that would be a good start. Let's say 384 divided by 5. That'll be a better one, right? So 384 divided by 5. Go ahead and pause that and do that now, just to warm yourself up, to refamiliarize yourself with the process of long division, because there's a lot of parallels between what we're going to do now and what we're going to do for regular algebra. Okay, so I'll go ahead and give you guys a pause now. Okay, so let's go ahead and start our lecture. So again, division of polynomials is very similar to division of real numbers, which is why I had you kind of on your own do a quick example for yourself, right? So when we evaluate a polynomial at a point, right, meaning when we plug in a value, we get a real value out. And that's true for any function, but really we're talking about polynomials at the moment, right? So if I plug in a real number to a polynomial, I'm going to get out a real number. So if I'm dividing two polynomials, I'm really just dividing two numbers, okay? It just so happens that the form of those numbers look like a polynomial, right? Because it works for any number, basically, right? So remember what we've talked about so far. When we've talked about algebra of functions, we've talked about the domain of a polynomial. I can plug in anything to a polynomial. There's no restrictions on the domain, right? So if I plug something into a polynomial, I'll get something out. So division of polynomials is really the same as just division of numbers. Just like factoring a polynomial is just like factoring a number, right? 10 times 2, or let's say 2 times 5 is 10. That's me taking a number and breaking it up into factors. It's the same thing with the polynomial. I can take a polynomial and break it down into its factors. So when we're talking about algebra on regular real numbers, right? If I have A divided by C, I will get some number out plus possibly a remainder. And that remainder is really a fraction of my divisor. So for instance, if I have 10 divided by 3, I'm going to get out 3, and I'll have a remainder of 1, but it's not 3 and a remainder of 1, it's 3 plus 1/10, right? I've almost made my way to what I needed to, but I'm 1/10 short. Right? Or I'm sorry, 1/3 short. So it'd be 3 and 1/3. So A is the dividend. It's the thing being divided. B is the divisor. It's the thing doing the dividing. C is the quotient. It's the whole number value you get out, the amount of times B goes into A evenly. R is the remainder. And B again is the divisor, right? So if you say, 3 with a remainder of 1, it's the same thing as 3 plus 1 with whatever the fraction is, right? So in terms of long division, it looks like this. A is what goes on the inside. B is what goes on the outside. When you divide, you come out with C whole numbers and a remainder of R. If you need to turn this back into this form, you write R over B to write it as a mixed number. Okay, so if we take the first equation and clear out our denominator of B, right? So meaning that we have an equal sign and two fractions, okay? Common denominator is the only denominator B, and we multiply each term by B. This goes to A, this goes to R, and this turns to BC. So what that means is that my original value that I started with before I try to divide is the same as my divisor times my quotient plus the remainder. Right? So again, when I had 10 divided by 3, 10 is what I started with, right? So B would be 3, C would be 3. 3 times 3 is 9, plus the remainder is 1. That would give me back to 10. Okay, so again, you did your own division. 384 divided by 5. You can check this same exact thing out with your example that you did on your own. Okay, so again, this is how we get back from our quotient back to our dividend. Okay, I know it says divisor, but it means dividend, right? So in function notation, we can write it in a very similar way. Our polynomial p divided by a polynomial d gives us another polynomial d plus some polynomial left over as a remainder divided by our divisor polynomial. Okay, or again, if we clear this out by multiplying times d, my polynomial is my divisor times my quotient plus my remainder polynomial. Okay, so this is going to help us to formulate some of the things we're going to be doing. So the algorithm for long division of polynomials is pretty much exactly the same as it is for long division of real numbers. Okay, so what we're going to do is we're going to look at the leading term of the divisor. That's what we're really focusing on, right? Remember, the divisor here is d of x. Okay, p of x is our dividend, q is our quotient, r is the remainder, right? We're going to determine what term is necessary such that the product of that term that we're looking for times d, our divisor, gives us the leading term of p of x, okay, if possible. So the coefficient here should be equal to or less than, but as close as possible, and the degree should match, right? So coefficient wise, it doesn't have to be exactly the same coefficient, but it should be close, okay? You'll see what I mean later. The second thing is we're going to multiply our divisor by the term that we identified in 1, right? The value that is the first part of our quotient. And we're going to subtract this resulting polynomial from p of x, right? The resulting polynomial being what we got when we multiplied what we found in 1 by the divisor. Okay. 3 is we're going to drop down the next term that we have in p of x, our polynomial, and we're going to repeat steps 1 and 2 with the result that we get in 3. So it's really a repetitive process. It's really just sort of 3 steps. Okay. We stop when we run out of terms. Okay. If our result is lower degree than my divisor, I can no longer find things to multiply to get to that value. Okay. Quick reminder is if there's a missing term, we have to use 0 as a placeholder. We can't just write out the whole polynomial without using a placeholder for the missing term. Otherwise, you start to make mistakes. It's probably the most common mistake for long division is not using this 0 placeholder, right? So let's go ahead and do an example. Okay, I'm sure all of that was perfectly clear to you. Just playing, right? So let's do an example because that'll make everything clear. So we want to find 2x to the 4th minus 3x cubed plus x squared minus 1 divided by x plus 2 by long division. The first thing we're going to do is set up our equation in the form that we need. All right, so notice here that there is no single x term with the power of 1. So we use 0 as a placeholder. That way we don't mistakenly bring down -1 for the place where we would have needed to pull down a 0. Okay. So the way we're going to do this is the exact same way that I described, which I'm sure you were probably not able to follow. So we're going to walk through the example very thoroughly, right? So I need to find a number to multiply times x plus 2 so that the first term here matches with this first term. Okay? I don't really care about the plus 2 part. That just comes along with it. I really focus on my first number. So I need a 2 so that this can be a 2. This is an x to the 4th power, so I'll need an x cubed. Okay? 2x cubed times x gives me 2x to the 4th. Now, one of the things that I said here, where I said it needs to be as close as possible so that the degrees should match, would be something like, let's say that this was a 3x, right? And this was a 2x to the 4th. Then I would have some problems here because my coefficient here would be larger. I can't have 3x and 2x to the 4th here and multiply it times the 2x, because then I would get, if this was a 3 here, I would get a 6x to the fourth, which would be too large. I would get a negative value out, right? So I have to be careful that I'm using values that so that I can try to get them to be the same as this, right? So that's a hypothetical. We're starting with a nice example, so don't worry about that right now, right? So again, x times 2x cubed would give me 2x4. So normally for a regular number, I would take this number, division-wise, right? I would take this number times whatever number I have dividing, and it would go under. So for instance, if this was 3, 8, 4, and 5, I would have a 1 on top, and then 1 times 5 would put a 5 under the 8. So if you did that example, that's what you would be seeing right now, right? But since we're polynomials, I can't just multiply 2x cubed times the first term and completely ignore this. I have to multiply both of these together. So what's going to go under here is going to go under the first two terms. It'll be 2x4 and 2x cubed times 2. So this will be plus 4x cubed. Okay, so that's what I get when I multiply 2x cubed times this x plus 2. That's what goes here, right? 2x cubed times x is 2x to the fourth. 2x cubed times 2 is 4x cubed. And I'm going to subtract that because I'm really focused on these numbers. I don't really care about these so much, but these are the ones I'm focusing on. I need these to cancel and be 0, so I'm going to subtract them. If for some reason this was like a negative x plus 2 and this value was negative, I would then add them together so that these two terms cancel each other. Okay, so if I am subtracting these right now because this is positive, right? So 2x to the fourth minus 2x to the fourth will give me 0. Negative 3x cubed minus 4x cubed will give me a negative 7x cubed. Okay, so here I'm taking negative this and subtracting this positive, so the signs change and I get a large negative. Okay, now I repeat the same process, but before I do that, this next term drops down, okay, to give me a matching binomial. Okay, so this is plus x squared. And do the same thing. I take 7x cubed negative, and I look at not the whole thing. I don't really care about the whole thing, just the first part. And I say, okay, what can I multiply times x to get negative 7x cubed? Okay, well, I already have 1x, so I'll need an x squared. And in order to get these to match, I need a negative 7. So my next term here will be negative 7x squared. Okay, because this times this makes that match. So now I multiply this number times the whole thing and it goes under, right? So negative 7x squared times x will give me a negative 7x cubed. Negative 7x squared times 2, this will give me a negative 14x squared under this term. And I'll subtract the 2 so that I can get these things to cancel, right? They're identical. To get them to go to 0, I subtract them. So for the first one, I'll get out 0, right? Because that's how I try to make this, was so that it cancel. So here I'll get negative x squared minus a minus, so that turns to plus 14x squared. So this turns into 15x squared. Okay. Same thing. This is why making a space was important, because if I didn't make a space, I would accidentally pull down this negative 1. But it's not the negative 1 that comes down, it's the 0. That's why the placeholder is important, so that I don't forget to put that placeholder there. Okay. So now I need to multiply x plus 2 times something so that x and the 15x squared match. So take a second. What do you think that value will be? You should have guessed 15x, right? So 15x times x is 15x squared. So that's my value. So I multiply 15x times this whole thing. I get 15x squared, 30x. Okay. So when I subtract these go to 0, and this turns into a negative 30x. Okay. So I drop down my negative 1. Okay. And then I say to myself, okay, what times x plus 2? So I'm only looking at x. So what times x can give me a negative 30x? Negative 30. Okay, so multiply the whole thing. Okay, 2 times negative 30 is negative 60. These cancel. Minus 1 minus a negative 60 gives me a positive 59. there's no way for me to multiply x times anything to get 59, right? Unless it's 1 over x, but we don't do that for polynomials. So this is my remainder, okay? So therefore, if I divide 2x to the fourth minus 3x cubed plus x squared minus 1 by x plus 2, my result is my polynomial 2x cubed minus 7x squared plus 15x minus 30 plus my remainder 59 over my divisor 59 over x plus 2. And that's how we divide polynomials, just like regular long division. It's just a little bit different because you have to incorporate this entire number when you put it here, but when you're trying to find the numbers that, you know, how many times does this go into that kind of thing, you're only looking at the lead value here to try to make things match up, okay? So that works all the time, okay? This works for any size polynomial. So what we're going to focus on now is synthetic division. Synthetic division is the preferred method of polynomial division, okay? It is the method I'm going to use all throughout this course. Whenever I make my calculus 1, 2, and 3 videos, I will be using synthetic division as well. Okay, so again, synthetic division is much more powerful. Although limited in scope, the conditions will always be met for the needs of this class, right? Maybe once or twice you'd have to do long division, but synthetic division is going to work pretty much all the time for what we need, right? So we'll discuss when we can't use it. So the algorithm is much simpler to follow than long division. Although, if you do long division a few times, long division should be easy for you because it's the same as regular division. It just can get really, really messy, right? That's really what the problem is. Synthetic division allows us to get the same result. The only limitation, though, is that the divisor has to be a first degree polynomial. You can only do this when it's basically a linear equation, right? So if any size polynomial divided by a linear binomial, that's the only time it works. So even if this was x squared plus 2, it wouldn't work, okay? So it always has to be a linear divisor. Polynomial size does not matter. That's the only time. So for example, if I had the same problem, but it was x squared plus 2x plus 1 dividing the numerator, I could not use synthetic division and I would have to use long division. Okay, so here's the setup. We're going to do the exact same problem, right? So let's talk about this first. So the 0 of my divisor goes in a half open box to the left of the polynomial. So for my example, remember x plus 2 is the divisor. The 0 of the divisor in this case would be -2, right? Whatever makes the denominator 0. Only the coefficients need to be written down, okay? So the dividend, the thing I'm dividing, I don't need to write it with the x to the fourth, x to the fifth. I just need the coefficients. That's all I need, okay? I put spaces between them, and I still need to use the 0 spacer. Very, very important to use the placeholder here, right? So the steps are, I start with drawing a 0 below the lead coefficient, okay? I'm going to add 0 to the lead coefficient, and I'm going to write the result below a line of equality. I'm going to take that result, and I'm going to multiply it against the value that is in that half open box, okay? That result then gets placed right next to the 0 above the equality line, right? I'm going to add again, and I'm going to do the same thing over and over again. It's actually very, very quick to do this, right? And I do this until I run out of coefficients. So again, the explanation probably sounds like crap, and you're like, what the hell are you talking about, Professor Williams? An example is very, very easy to follow, okay? The last term that we get out is the remainder. So let's do our example. We'll do the exact same problem. The 0 of my denominator is what I'm using. I'm going to use -2, right? The 0 of x plus 2 is x equals -2. So I do a half open box, and I put -2 in that box. This is in the corner. I'm going to write the coefficients of my polynomial on the same line, but to the right of this box. So 2, the next one is -3, the next one is just a 1. I have a 0 placeholder and a -1. Okay, I write 0. I always start with 0, and I write it just below the lead coefficient. Okay. I'm going to have a line of equality, and I will always be adding. So whatever I put here, I will continue to add. So 2 plus 0 is 2. So I write 2 under the line of equality. Then I take this value and I multiply it times -2. Okay. And the answer to that, 2 times -2, I write in the next line, -4. I do the same thing. I add these together. I get -7. And then I multiply these two things together. So -2, -7 is 14. That goes here. Okay. I add these together. I get 15. I multiply 15 and -2, -30. Okay. 0 plus -30 is -30. -30 times -2 is a positive 60. Add these together and I get 59. Okay. Now what we have here is our answer, right? So before we go into that, I know this wasn't a very long example, but in order to do this algorithm, it actually can go by very fast, right? So I try to go slow. So let's kind of go just one more time from the beginning, okay? -2 is the value I use. I write my polynomial, okay? I have my placeholder for anything, any power that's missing, okay? I always kick it off with a 0. I'm going to add them together. So it goes very fast, right? 2 plus 0 is 2. Times that is -4. Add that is -7. Multiply that is positive 14. Add that is 15. Multiply that is -30. Add that is -30. Multiply that is 60. Add that is 59. It really goes that fast. So at this point, majority of the time, I can divide polynomials as fast as I can write, right? It really doesn't take a lot of thought. As long as your addition and multiplication is okay, this goes pretty quickly, right? So it took me a lot less time to do this twice than it did for me to go over this method once, right? So boom, boom, boom. Okay, we get our answer. So that's our answer. So the last term is our remainder. Okay, it's always the remainder. From the remainder, I count up. Whole numbers, or coefficients I should say, right? This is the real number, my constant term, power of x squared, power of x cubed. Okay, I should end 1 power less than what I started with. If this is an x4, I'm dividing by a first degree polynomial, right? My result will be a cube function. So this will be cube, square, x, constant, remainder. So either remember the power that you had and the power you should have when you go this way, but I generally like to work from the end, right? My remainder, my constant, x squared term, x cubed term. So when I write this, I have 2x to the fourth minus 3x cubed plus x minus 1 over x plus 2, right? Is the same thing I had before. 2x squared minus 7x squared, 15x minus 30, and then my remainder over my divisor. This is the exact same thing that I got for the other answer. Okay, 2, -7, 15, minus 3. Right. So the values that we're getting when we're doing that long division, so the 2, the -7, the 15, and the -30. Right. So it's the same thing that I'm getting before I I'm sorry, the 4, the 14, the 30, and the 60. That was what's inside of my synthetic division, right? I had 4, I had a 14, I had a 30, and I had a 60. Okay. A 4, a 14, a 30, a 60. Okay. One more time, just so that you're clear. That's that secondary value that got worked in. Okay. So that's how that works. Synthetic division is very, very fast, very thorough. It allows us to do a lot of stuff. Okay. So again, note that the degree will be 1 less than what we started with, and that's because we're dividing by a first degree polynomial, right? The term that we get in the end, okay, even if it's a 0, then it's a remainder of 0. But this will always be our remainder, right? The first term after our remainder is always the constant, and then the x, and then the x squared, and so forth, as I walked you through, okay? So a very nice theorem that goes with this, that helps us out a lot, is the remainder theorem, where we're talking about the remainder. So what the remainder theorem basically says is that when you do long division, the remainder, we'll go through the thorough definition, but just as like a Cliff's Note version, when you do synthetic division, or even long division of polynomials, your remainder value is the value that you would get if you were to plug in your divisor's 0 into the polynomial. Okay, so what that means is if I were to plug -2 into this top polynomial here, I would get out a value of 59. So if I put 2 times -2 to the 4th minus 3 times -2 cubed plus -2 squared minus 1 and evaluated that, comes out to the exact same value as the remainder of my polynomial. It's a very, very strong theorem, which we're going to use quite a bit. So here the formal definition is that if the polynomial p of x is divided by this linear, right, in this case it was x plus 2, is divided by this linear polynomial, right, then the remainder of the division is p of c. Okay, so the remainder would be the same exact thing as if you were to plug c into your polynomial, right? The factor theorem. If p of c equals 0, meaning if the remainder is 0, okay, or I'm sorry, if you were to plug c into your polynomial and get 0, right, it would be the exact same thing as having c as a factor of your polynomial, right? So the factor theorem with the remainder theorem is extremely powerful. So what this is saying to us is that if we do long division, if we do the synthetic division, and we get 0 out here, a remainder of 0, that means that this factor cancels with some factor above, okay? It means that this is a 0, it's one of our factors of our polynomial, okay? If p of c is 0, then c is a 0 of our polynomial, and x minus c is a factor of p of x. So if I do this long division and I get 0 out, then that means that c is a factor from our polynomial. So let's do an example. Let's evaluate p of -2 for that polynomial that we've been working with so far. Okay, we already know what the synthetic division looks like without going through it, right? What this means is that if I plug in -2, I will get out 59. So let's check it the long way. If I plug in -2, okay, this will be 2 times 16 minus 3 times a -8 plus 4 minus 1. Okay, so again, 2 times 16 minus 3 times -8 plus 4 minus 1. This is 32. This is positive 24. Okay, plus 4 minus 1 is a 3. So if we add these together, 32 and 24, that is a 56. 56 plus 3 is 59. Okay, it takes me a lot longer to plug this in term by term than it did for me to do the synthetic division, where I start with 0, 2 times 2, -2, so that's a -4, -7, 14, 15, -30, and so forth. Okay, I'll fix this. You guys saw that I did that earlier, so I'll fix that later. All right, example. So we want to find a 4th degree polynomial that has zeros at x equals -2, -1, 0, 3, and such that a2 equals 2. So we're given the zeros of our polynomial, and we're asked to adjust our polynomial so that the a2 term equals 2. So first things first, I'm going to write this in its factor form. Okay, so the general form of this polynomial in factor form is going to be p of x equals a, because I don't know what the lead coefficient is. I have x, because that's one of my zeros, x plus 2, because this is a 0, x plus 1, because -1 is 0, and x minus 3, because 3 is a 0. Now, when we do this, do not just try to leave this for me in this form. You have to expand this out. So we're going to multiply all of this out. Okay, so first I'll start with these two. You get x squared minus 2x minus 3, right? Because 1 plus -3 is -2. 1 times -3 is -3, so there you go. Next, we will distribute this x plus 2 across this polynomial. Okay, so you got x squared times x plus 2 minus 2x times x plus 2 minus 3 times x plus 2. We can simplify that out. Okay, so I did it all at once. So x squared, 2x minus 2x squared minus 4 minus 3x minus 6. Okay, that's what we get when we multiply that out. Right. The next, I'm going to distribute this ax value, combine my like terms and distribute that out, right? So here we see that for the x squares, we have 2 minus 2 means that they go away. Okay, here I have 4x minus 3x, so that's negative 7x times this x gives me that 7ax squared, because this gets bumped up by this value of x, and then 6 turns into an ax from this value. So I want my a2 term, right? I said I wanted it to be 2. This is my a2 term. So I set negative 7a equal to 2, and I solve for a. So that's negative 2, 7. So now I plug in negative 2, 7 everywhere I see a. And that gives me a resulting polynomial of negative 2 over 7, x to the 4th, minus, here in this case, positive 2, right? Negative 7 times negative 2 over 7. The 7's cancel. The negatives turn positive. And then here, this turns into 12 over 7, because 6 times 2 is 12 over 7. Negative and negative is positive. So that's my polynomial. Okay? That results from that. And that's it, you guys. That's how we do with polynomials. So synthetic division, and then using the given zeros and any other information to find the standard form polynomial that satisfies those conditions. So this is the polynomial right here that has x equals 0, x equals 3, x equals negative 1, and x equals 2 as a 0. Okay.